Red Sox. Yeah. The best like season ever was like 116. Yeah, so that's like no one wins that.
Yeah, make sure you post
Now people start well, they're the Canadian.
No, that doesn't.
Yeah.
So how was test two?
Hard.
It was hot?
Not enough time.
Too long?
Yes.
We hope to return that to you on Thursday, the day after Halloween.
Oh yeah.
Oh yeah. What? There's no homework due today. I'll give you a break. Yeah, I thought after the test, maybe you can catch up on other things. So we're going to start a new chapter today. As the last major topic for the remainder of the semester are two areas. One is chapter 9 on viscous external flow. And I'm going to give you some of the background by using previous homework problem to set the stage. The second topic is more differential analysis. It's in chapter 4, so we're going backward. And the intent there is to develop an equation for viscous flow. So you see the equation of Euler for invisible flow, and to finish the entire semester, we're going to spend a good deal of time looking at how to derive the equation for viscous flow. And then upon doing that, we're going to use that set of equations to do more rigorous analysis on the concept called the boundary layer. And that's the end of the semester. So remaining about 4 weeks of lecture is all that we have time for to cover some more intricate and in-depth topic. So we're going to start one of the two topics today. The agenda listed here is we revisit the concept of boundary layer. What is, how we can make use of that concept to analyze fluid flow problem. And then drag coefficient is something you have seen in dimensional analysis. What we'll do now is to look at how the flow will affect the drag coefficient. What is meant by concept of nice separation? What is meant by frictional drag, etc., etc. And And we will also discuss very briefly today the concept of the thickness of the boundary layer, and that is enough for the homework that's to be due on Thursday. So the reading is chapter 9, a new chapter on viscous external flow. Homework, while there are 4 problems, they're not in depth, they are very elementary concept type warm-up exercise. Problem 9.4 are both the new edition, which you have, the 8th edition, and Mike will post the 7th edition on Canvas so you know the problem statement. And there are 2 other problems, 25 and 26. Only one of that I will touch on in class. The rest of them are very introductory type homework problem. And then another set that is due next Tuesday. All right? So that's basically the move forward plan for today's lecture. Any questions before I start? Okay, so I want to pull together a couple of the previous homework, starting from the beginning of the semester, to help refresh our memory of what we call viscous frictional effect. First, we start with the concept of viscosity, which is something you have seen in 21-24. Conceptually, is a stationary lower plate and a upper plate that is moving at a constant velocity v. And we know a condition called low slip, meaning there's no slippage between surfaces of a stationary surface and the fluid. If this lower surface is not moving, the fluid particle immediately above this surface cannot move also. And that's what we call the low slip condition. Contrary to that, on the upper plate, if it's moving at a constant velocity v, then the fluid immediately below the upper plate must also move at velocity v for the low slip condition. Yes?
So if I had like 2 solids, one was sitting on top of the other and I pulled one,
Okay.
there would be no, like, they would slip. Like, there would be no slip condition.
2 solid, no fluid.
Right.
Okay?
So I guess my question is, under what conditions is there some slip? Like, how
For-
accurate is it to model it as no slip?
So for solid, it's totally different.
Right.
For 2 solid, you're going back to your solid mechanics. And the fact fluid is continually deforming. Remember what we talked about?
Right.
Make it a subject of study all by itself. So whatever concept you have applied to solid, how it deform, how it slip and no slip, have no direct application to a fluid. And what we're talking about is not 2 solid in contact, but much rather the fluid now trapped in between 2 plates. And that interaction between the fluid and that solid is totally different than 2 solid by themselves. So you can't draw an analogy between the 2 cases. Obviously, if you have 2 solid that you're gliding on each other, they will deform, they will shear, right? But fluid had no such property. It will just continue to shear. And hence, you have the lower and upper no slip condition that dictate how the fluid in between the 2 plates will behave, right? So in this simplified example, we have introduced the concept of viscosity. That's just a recap of what we did way back in 21-24 as well as the beginning of the semester. Now we're going to focus for the next couple of lectures how this viscosity will influence the fluid behavior between these 2 plates. Or in the case of external flow, how it will influence the development of something called the boundary layer. Chapter 8 for internal flow. And here's an example. Of the boundary layer, and now we'll come to the internal flow later on. So you have this problem back in chapter 5 for continuity, of which you have a jump due to hydraulic that you have a water flow over a channel, open channel, meaning the surface of the water is under atmospheric condition, just like you saw on a faucet in the kitchen hitting normal to a plate, the water can jump. And in this homework, back in chapter 5, you were told that the velocity profile or velocity distribution, u being a function of y, and y is the vertical axis, is given by a parabola. 0 at the wall, for the same reason, no slip, and maximum at the free surface. And this profile of velocity is now what we're going to study. Under what condition will it be parabola? Are there other cases that the velocity profile will be different? The answer is yes. Depends on the state of the boundary layer, whether it's turbulent or laminar. But back then, the only concept I stress is, again, the low slip condition. But right now, we're going to do a deep dive. And when we're done at the end of the semester, you will be able to analyze this boundary layer profile. And under certain conditions, you can use those information to deduce or estimate the shear stress at the wall. And that's critical, as we'll see later on, that's what led to drag of an airplane cutting through air. Okay, so that's another example of how viscosity and the concept of boundary layer come into play. And furthermore, 2 more examples to at least set the stage so you can revisit previous concept. Again, for both problem 522 and also problem 572, you're dealing with non-uniform velocity profile. In this case, the laminar flow in a pipe. So Reynolds number less than, say, 2,000. And you were told the velocity in this circular pipe is also a parabola. And it happened because of the viscous effect of no slip at the wall. Of which, for both of these problems, if you recall what was asked of you, is to use continuity for this problem 22 to estimate the average velocity. And in this case here, estimate also the average velocity and the average momentum based on this profile. And lastly, in chapter 8, we briefly touch on what we call the entrant flow in a pipe. Where invisible to our eye, you have this dashed line that dictate the development of the boundary layer due to viscosity. And again, the no-slip condition is what we are employing to allow us to determine how the flow velocity will develop as we go down the axial station. And this inviscid core is where you can pretend or neglect the viscosity only at the entrant region. As the flow continues to go downstream, eventually that boundary layer will meet and the entire flow become fully developed. And that's what we studied in chapter 8 for most of the chapter. And this entrant region is where the development of the boundary layer become important. And those are the details that we are now going to dive into. Give me a flow condition, can I estimate the thickness of the boundary layer, and more importantly, the shear on the boundary layer due to this viscous effect. And from then I can deduce the drag, and so on and so forth, and analyze the problem. So that is a backdrop. Now we can look at what are some of the more interesting elements that we want to study for what we call the external as opposed to internal flow. The difference between this and the internal flow is that the internal flow is wall-bounded, meaning flow in a pipe. Flow between two parallel plates, which we will study academically, versus an unbounded flow that is over a sphere, an airfoil, we call flow about an immersed body. Flow over the chimney of the power plant. At 150 miles an hour wind, can I estimate the forces on that chimney? Will it collapse? An automobile, if you work for Ford or GM, and there are wind tunnel to test to validate the analysis, you're going to have to analyze the flow over the automobile. And it consists of both external and internal flow when you think about that, right? The external flow is the flow going over the upper body of the automobile, where the flow is not bounded. But between the automobile and the pavement and the road, you have both the underneath surface of the vehicle and the road itself. So that is a wall-bounded flow. So if you're an engineer at GM, you will do analysis on that flow using something called computational fluid dynamics. And you're going to analyze a very complex aerodynamic body cutting through air, but on one side is bounded by the road, so it's wall-bounded flow. The other side is not bounded like an airfoil. There's no presence of adjacent wall, and it has that characteristic that make the boundary that behave a little differently. So that's the kind of problem we're trying to tackle that will prepare you for a career that analyzes fluid flow. So as another example, later on, we're going to look at why there are dimples on a golf ball. What does it do? For what purpose? And we're going to look at very briefly why this fish has a streamlined shape. For what purpose? So those are the elements or pieces of information that we try to address and answer using concept of the boundary layer. So very quickly, just introduce some of the terminology that we'll be using throughout the chapter for any immersed object like an airplane wing, airfoil, a sphere or cylinder, and in the case that I mentioned, that is a combined problem of both internal and external flow, an automobile. So I have both external flow on the upper surface and wall-bounded flow on the lower surface. All of this I'm interested in estimating two things. At the end of the day, as an engineer, my job is to estimate the so-called drag force component parallel to the flow. Because for an airplane, that's the power propulsion device I have to come up with to move the airfoil to cut through air. The component perpendicular to that, which we have also looked at, is called lift. So when we are all said and done, those are two end products that we want to be able to estimate as an engineer. And for this part of the lecture, for today and also on Thursday, we're going to find that most of this coefficient of drag and lift are determined experimentally. And you just be able to use those data very carefully to estimate those forces. Yes?
So if you took like an airfoil and flipped it upside down,
Mm-hmm.
then the force would point downward instead of upwards.
So that's a very common question.
So is that negative lift?
Yep. So if you fly an airplane upside down, right, does it mean the airplane will always plummet to the ground because now the lift is pointing towards the ground? The answer is it depends on the angle of attack. Right? So not categorically that the airplane is flying upside down will always generate a negative lift or downward force. So it's a very simplistic picture I'm presenting to you. All this lift and drag coefficient will be presented as a function of how the flow is approaching the airfoil. And for other subjects as symmetrical, it may not matter, but for an airfoil, that's critical. So at a limited orientation, an airplane can fly upside down. All right? Fair question. Okay, so that's just a very brief introduction. But the concept that we have to be careful with in bookkeeping is now the introduction of a term called pressure drag. So there are two effects that led to those drag and lift. What do I mean by that? Shear is purely due to frictional effect like we dictated on the right-hand side. A plate that is stationary and creating a velocity profile will generate some type of shear purely due to friction on the surface. And collectively on the plate or on an airfoil, collectively all those shear from the leading edge to the trailing edge add together will give me the so-called one component of the drag force. Frictional driven. But there's another one that we loosely call a pressure drag. That is due to the difference between the forward and the